But let's talk about Amperes Law. Now, my students have been wondering about, or wanted to learn a little bit more about Amperes Law and where it came from and how do we use it, and maybe just get some more practice with it, see some more examples. Physics! The one and the only Physics. Welcome to the channel. Thank you for the follow. We're a huge fan of yours. Okay. Get it? Because we like physics. Anyways, I got bad jokes. Welcome to the channel. Let's see. So Amperes Law was first written down. So I have a little history for you. Was first written down by James Clerk Maxwell as one of the 4 Maxwell's equations, and we're going to see that at the very end. Because at the very end, I'm just going to do a tidbit. Hey, Loza, good to see you. At the very end, I'm going to do just a tidbit of Jackson, just for those who love Jackson like I do. It's not long. It's very, very short tidbit. But Jackson has a brilliant little conversion from the Maxwell's equations into Amperes Law that I thought I would show. Now, the way that James Clerk Maxwell did this is he took the work of a guy by the name of Ørsted. I think that's how you say it. It's the O with the slash through it. Looks like this. Ørsted and Ampere. So he did take Ampere's work on the forces. Ørsted found that there's currents. There's a magnetic field from, actually instead of writing magnetic out, we should write B field. Ørsted figured out that there's a B field from current carrying wire. Then Ampere was the one that discovered that he did the B field force laws for these, B force. Isn't that a show about mice or something? B field force laws. Okay, now, then what James Clerk Maxwell did is he was able to combine these two people's, Ørsted and Ampere's work to come up with Amperes Law, which is what we're going to talk about today. Okay? So that's a little history on what happened. Now, there it is. G-force. Oh, it's about guinea pigs. Yeah, that's the one. Okay. Now, all right, so do you remember Biosavart Law? So let's write down Biosavart. Now, Biosavart is a lot like, and I'm going to be making a lot of comparisons to, the E field, electric, the electric field, and with the magnetic field. And the Biosavart has a form. It looks like this. It's some infinitesimally small magnetic field is equal to mu sub naught, which is the vacuum permeability, perma something, times the infinitesimally small charge times the velocity vector across the radius direction. See how it's r hat, that's a unit vector, it's in the direction of the radius, all divided by r squared. Now there's another version of this that you might recognize, which is mu sub naught over 4 pi r. 4 pi r squared, and the current times the infinitesimally small line segment crossed with the direction to the point of interest. Oh, and you can see that these two are kind of the same thing, right? We can get from one to the other kind of simply, right? We know that the current, and for my students, I guess you might not know quite yet, but you'll know soon, that the infinitesimally small charge over the, change in charge over the infinitesimally small change in time, dq dt, is how we define the current. Permafrost. Yes, wrong classroom. And we also know that velocity is equal to, some very small change in space over a very small change in time. So it's easy to see that we can just swap these out. This one for this one, for this one, for this one, in this fashion, right? basically the idea would be solve for dt. And what do you get? Okay. Now, so we can switch these around, but this is the Biosavart Law. Now, this is really nice, and it can be you can solve any magnetic field with this, right? Yeah, you can solve any magnetic field with this, but the integrals can get really messy really quick. And that was just kind of the same thing for Coulomb's law, right? When we wanted to find the electric field at some point away from even a line charge, it could get very nutty if you had to do multiple dimensions like x and y, right? Then you had these like giant integrals. You had to do either trig substitutions or integral tables to solve the integrals. You had these really messy looking like things. I'm sure my students remember that. And so we ended up using Gauss's law, and then it became like a two-step process to find the electric field out from some line charge. Or you could find the same thing with like a sphere or something like that. You could find it all with Coulomb's law, and you can find the magnetic field of any shape with Biosavart. But the integrals are going to get really, really messy. So similar to this, we will want to use symmetries and figure out a more sustainable or easier law to use. So we're gonna find that law is Amperes law. All right. And there's no surprise that Amperes law kind of follows a similar pattern. Like I said, we're going to be drawing a lot of comparisons between Amperes law and Gauss's law. And but before we get there, let's first start by talking about what a line integral is. You'll need line integrals to solve Biosavart's law. To solve Amperes law. So let's kind of define what they are. And then we can move into actually incorporating the magnetic field. What am I stuck on? Okay. So if we were to have some line. Now, I think one thing that I have to emphasize on this a lot is that this is just not going to be a current carrying wire. Okay? It's very easy to get some mistakes and to start thinking that this is a current carrying wire, but it is not. It is just a line in space. And we're going to break this up into tiny segments. And we're going to give them some length, but it's going to be very small, so we're going to call them delta S. And more so, we'll just call one specific one delta SI, or delta SK, whichever you want to do. And there's two ways we can solve this. We could also make this, instead of making it some distance, we could make it infinitesimally small. So ds. So we'll say, okay, now we have it's as small as you can possibly think. It's infinitesimally small. And then one way to make it into a line is by integrating it and blowing it up into the size of the line. And we did this a lot like the first day, right, of our discussion class. But anyways, we can figure the length out, which is equal to the sum over all of these chunks of line, the small chunks, right? And like I said, with some length to it, we can just sum over them all. We can figure out something that approximately looks like this line. But if we wanted to be exact, we could actually just take the integral from the initial to the final of one of these infinitesimally small points. And basically what we would do is take this anywhere along the line, take this infinitesimally small point, and integrate it or blow it up into the length of the line. And all of these equal the length of the line. So this is all well and good, but this is not what we need to do. But this doesn't have anything to do with the electric field, right? Or the magnetic field, excuse me. So we now need to figure out how is this helpful in the magnetic field. Well, suppose you have this line, right? And now we're going to introduce some B field, right? So there's going to be some B field that washes over it, right? And the idea is how, if we were to take some piece of a line, let's take this piece right here and enhance. Enhance. And you're going to get some piece of line like that and some magnetic field that's going to brush up against it like that. There's going to be some angle between the two. We'll call it phi. And if we want to figure out the contribution from the B field that's going through the line, then we could call that the dot product, right? So if we were to have this segment right here, we're going to call this our small piece, right? Delta SI. Then we could sum up all of the overall i's. All of the times that we have those very small pieces, there's going to be one piece of magnetic field. And if we dot it with this little chunk of line right here, then we can figure out the contribution of the magnetic field on that line, right? Motorcycles. Enhanced edition, exactly. If it was, we remember our dot products to be, B, magnitude B times the magnitude of delta S times the cosine of phi. Okay, right? Like that's the definition of the dot product. So if we sum over all of these, we can actually figure out how the magnetic field is at every single point along the line. Okay? Just by using this dot product, projecting the magnetic field onto the line segment to figure out how much magnetic field exists on the line. Now, of course, this is good for the little small chunks, and we can sum them all up, or we can integrate them, right? So we can do the integral from the initial to final of the magnetic field dotted with this infinitesimally small line segment. Okay? So now, if you know Amperes Law, you can see it's starting to form. But it's the same concept, right? We can take this now, and instead this is our infinitesimally small piece of chunk of line, and we are going to, project the magnetic field onto that line and figure out how much of a contribution that magnetic field has on the line. And since it's infinitesimal, it can be pretty much exact. And then we can take that and integrate it into the length of the line. Right, so let's take what Justin said and let's apply that by kind of being a little bit specific with what dot products.
From reality.
Thank you, Admiral. So let's take what Justin said and let's be kind of specific, right? If we have lines, right? Then what we want to do is we want to say, like, okay, if we take this magnetic field, it forms a right angle, right? So anywhere along here, if we were to say that this is the B field, so now we're talking about orienting our lines, orienting our line with the magnetic field that we're given, right? Kind of like we did with the flux and the electric field in Gauss's law. So now if we take this, then if you were to try to take some little tiny dot right here, we'll call it ds, and you try to dot the magnetic field with ds here, you're going to get 0. Right? Makes sense? Anytime you take this dot product and the angle right here is 90, it's going to be 0. Now, if we want to do the same, so we're going to say, well, okay, so that's going to be 0. So if we, so then what do we do if it's tangent at every point? Let's do blue again. I don't know why I stuck with white. Let's do blue. So now if we pick a line, if we pick the magnetic field that's tangent at every point, then what happens when we take this dot product is it's always going to be the following. The integral, I know I didn't do the integral here, but it's 0 regardless. Okay, so now if we take the integral, right, of the dot product, b dot ds, then this will always be equal to the magnetic field times the length of the wire. Why? Well, because this theta is always going to be 0, which means the cosine of 0 will always be 1. So you're going to get the maximum contribution of the magnetic field, right? So you get all of B, and then the only thing that you have left to do is take the integral from, this initial point to this final point, and you get the length of the line, okay? So this is a line integral, and this is the line integral when we consider the magnetic field along that line. Okay, next step. So now let's talk about a current carrying wire. So if you know this is a current carrying wire, the direction of it is given by the X or a dot. This is into the board, this is out of the board, okay? So now, as our friend Oersted found, that we can figure out the magnetic field around this with some R, right? So there's a magnetic field around this, but in order to do that, let's just say I want to do a line around this a closed line, and at any given point on that line, there's a tangential magnetic field. Right? So, flip the page. So integrating over this whole circle, right? If we were to just take some random piece of line right here and call it ds, we can integrate over this whole circle, and this is the integral sign for integrating over a closed circle or a closed loop. Will give us, again, notice how, again, like the dot product at every single point here, the magnetic field is tangent to this line. We did find that out from what Orsted taught us. And then we can find out that this becomes b times the length, right? We said that last time. If it's tangent at every given point, then the theta for every given point will be 0, cosine will be 1, and it's just going to be integrating over the length. And the length of the circle just happens to be the circumference. So b times 2 pi r. Now, we can also do, we also found, you can find it on your own if you'd like, but it's the integrals can get a bit tricky. If you have Randall as a textbook, he does it for you in one of the problems, or in one of the examples, I mean. But you can find the given magnetic field of an infinite wire to be b is equal to mu sub naught I divided by 2 pi r, where this is the current running through the wire. Now, this will tell us, if that's the case, that for this example, if we were to take the line integral with respect to s, that this is equal to the mu sub naught, which is the vacuum permeability, times the current that you enclosed with your loop. Would B vectors cancel each other out if the two wires had current flowing? Yes, exactly. Yep. That is exactly true. QST. It depends on where you measured it, though, too. That would be a lot. It'd be like if you were to talk about the middle right here, then yes. But if you were to do, like, you could actually figure out the force from one wire onto the other wire and everything like that. But it depends on where you were. If you were talking about right in the center, you'd have one that was going like this, curling around this way, and one that was curling around this way using the right-hand rule. So one's going this way, and the other one would be going this way at this point. So those two would cancel out at that instant, at that point. What was your time about? Oh yeah, so there we go. Now we actually see Amperes Law, but can we talk more about it? Like, what is it, right? Well, so this is, again, we're going to kind of draw a bunch of similarities between this and Gauss's law. In Gauss's law, we had an E field, right? And the way that we started learning about the E field in Gauss's, and if you take introductory physics, you're always going to learn it this way, is, oh, I think so at least. It'd be weird to learn it another way. But you have some E field, and then you usually start with shapes, right? And you say, okay, well, what's the flux through this object, right? What's the flux of the E field through this object? And you find the flux first. And then you say, okay, well, now if the flux is equal and outgoing through an object, right, then we can use Gauss's law to figure out use symmetry, I should say, to figure out, make some shape. So say we have, like, some charge here. We can make some Gaussian spherical symmetry around a charge, a point charge, and find that the flux through our imaginary shape will always follow the rule. Let's write it all out in its glory. Is equal to the integral of E dot dA, which is equal to Q enclosed epsilon naught. Well, now we have this one, right? We'd have this law. But then under the same guise, you could consider a closed loop and finding the magnetic field through that closed loop. And it reaches the same, you reach the same conclusion, right? And these are the following three things. Bye, Blake. Have a good class. What the flux? Another good t-shirt? Those are good t-shirts. So there's three things that we can talk about with Amperes Law that are true, and they follow the same way that they do in Gauss's law, right? And that is basically the following. The total amount of B field through a closed loop doesn't change, right? The closed amount of, or the total amount of B field through a closed loop doesn't change. It's always going to be equal to mu sub naught times the current enclosed. Okay? Now, you know, of course, with this ds on this side, right? And then that is true independent of the shape of the Amperian loop. You could have a series of wires, you know, and have an Amperian loop that looks like this, right? Where ds is now going to be the shape of this weird loop. That's true for any shape. Oftentimes, like we did on Sunday when we were trying to build stuff, we did a square loop, right? A square loop through a solenoid. We had a bunch of wires that had current running through them, so we did a square loop through them, and we found out that since this and this, when you dot them together, that gets to a 0. This had no magnetic field contribution because it was outside the solenoid, and we had a bunch of cancellations, and so this was the only thing left to consider when we did our dot product, right? So there's a bunch of different loops you can have. Oh, let's just leave that up for a second. Hi, Dr. Derp. Good to see you. Good to see you. Wow, that's super important for my work. I'm measuring electromagnetic fields of the electricity grid. Wow, yeah, that is good. It might be a little bit more complicated than this, though. But that is good. Definitely good. Cool. Isn't there another math theorem that is closely associated with this law? Well, maybe. Besides Gauss's law. I mean, like I said, those two like kind of go hand in hand, Amperes Law and Gauss's law. But there's, we'll see the Maxwell's equation soon. Maybe that's the one you're talking about? Admiral HB, do you know of something different? All the vector identities. Like, Stokes' theorem, and what's the other one? There's a couple of them. Anyways, let's keep going. Okay, so this is independent of the shape of the Amperian loop. We can pick different shapes. This is independent of the amount of current that goes through, right? Or I'm sorry, excuse me, of where the current goes through, right? So here we have some odd shapes, but it doesn't matter that one's here, one's here, one's here. As long as it's enclosed, it counts, and it counts the same. The Amperian loop symmetry takes care of that for us, so we don't have to worry about it too much. Differential forms and Stokes' theorem there, yeah. That's what we're going to see in a second. I just use the tools. That's awesome, Edgar. No, that's super important, though. Super, super important. And then it only depends on what you close inside the loop. So, for instance, for our square loop, it completely depended on how many of these wires we wanted to carry in. Ultimately, we wanted to enclose the entire solenoid. So it was completely dependent on how many wires we enclose is how it will affect the magnetic field from those contributions of wires. Now, okay, so I think we're going to close with an example of this, and then we're going to do a quick, just a little primer based off of Maxwell's equations from Jackson, which we all know and love Jackson from graduate E&M. And he has a great little 2 or 3 step process to show how you get Amperes Law out of the Maxwell's equations. So let's erase this. We'll do our example. I like greens. Maybe this different one. Okay, so let's do an example. A wire with radius R carries current I. Welcome to the channel. Find a little bit weird. The B field, the magnetic field, inside the wire. So where are we looking? We're looking at the R, which is the R from the Amperian loop, less than the R of the wire. Cloned Kitty, thank you for the follow. Welcome to the channel. Okay. Now, firstly, we have to extend, and this is the same. Oh, we want to do the strength or the magnitude. Now, what we want to do is, this is my two-step process, and I always do it for every Gauss's law and Amperian loop problem. So hopefully, I don't know which way you guys are taught, but I kind of have, like, if you're my student, you know that I have like certain ways of doing things. The solving force problems is always a three-step thing. Free body diagrams, write out the sum of all the components, and then solve the system of linear equations. Gauss's law and Amperes law is first we establish what the E field or B field is anywhere. Okay, and we use Gauss's law, or Amperes law in this case. And we start here, and then we know that our symmetry for this is a wire, so we're just going to use our Amperian loop, our nice circular Amperian loop. And we know that the magnetic field is tangent at every point on that loop. So this will simplify into 2 pi r. This will give us our mu sub naught I enclosed on the one side, and b times the length on the other. So of course we get our nice b is equal to mu sub naught I enclosed over 2 pi r. So that's the first step. Find out where the b field is always in terms of your I enclosed. And if you do the Gauss's law, it's in terms of and if you do Gauss's law, it's in terms of Q enclosed. Then we have this, so now it's by case value. So like for this one, we only have one case to do, and we want to do the case when R is less than big R. So inside the wire. So let's draw a little picture really quickly. We haven't done that yet. If this is the wire, it's going to have some radius big R. And inside the wire, this is our first case. This is our Amperian loop with little r. Right? So now this is our first case. Little r is inside big R. If we had a second case, one might be like, define the Amperian loop out here. Right? And that might be another one, but we're not worried about that case. That one would be rather trivial in this case too anyways. I'm going to say guru. Maybe I got that right. Maybe I didn't. Welcome to the channel. Thank you for the follow. So where are we at? So we have our B field. So now, like I said, this is true everywhere. So we're going to start with it. But we're not quite done with it, right? We need to find I enclosed, right? Because we're not allowed to leave things in terms of solid state and QFT. It's like magic. So I enclosed it. We need to get that in terms of I. Okay. How do we do that? Well, just like Gauss's law. You're going to be sick of me saying it. But it's true. We're going to use some sort of density. Right? Why? Because densities are this nice thing that's going to relate the entire thing. So we have, for current density, we have the total current over the total area versus something that we have inside of our Amperian loop. So inside of our Amperian loop, we have I enclosed and the area enclosed. One can think of the area enclosed as just this part. This part is enclosed by our Amperian loop, right? Radius r. So this part is enclosed by our Amperian loop, and that's also what we're going to need to find I enclosed. J is going to be the connecting constant that connects the total current with the total wire, and the area enclosed with the current enclosed. Now, that means that I enclosed is just going to be the current times the area enclosed. Actually, let's rewrite it kind of bigger. Let's write it over here. That means that I enclosed is going to equal, so we're going to multiply this up here, and we'll get I, the total I times area enclosed divided by area total. Let's simplify this. That's going to be the total current times pi little r squared for our area enclosed divided by pi big R squared for our area total. The pi's are going to cancel away. And now we have a formula for our I enclosed that relies on everything that we have. So for any r that's smaller than the large radius, or the radius of the wire, we have mu sub naught times I times r little r squared, all divided by 2 pi r times large R squared. We can simplify that one more time by getting rid of the extra little r's that exist both in the top and the bottom. And we'll get mu sub naught I r divided by 2 pi big R squared. Is that what I have here? Yeah. And we've done it. But yeah, so here we are. We've found the magnetic field for the case inside the wire. Now again, if we wanted to find the magnetic field outside the wire, it's a little bit trivial because I enclosed is just I. So that's it. That'd be the end of it. All we have to do is set I enclosed equal to I, plug it in, and we're good. Now, but yeah, so you do case-by-case basis. In each case, you have to reconsider what the I enclosed is, and that's how you find the magnetic field at that case. My minions. Now, there's one more step to this fun little thing, and that is, let's take a look at what Jackson has to say about it. Again, I will be putting this up on YouTube later. !YT for my YouTube channel. I have a couple discussion series, including path integration, our general relativity one, which takes place Friday, which we'll be picking up again on Friday, this Friday, and then the Lagrangian mechanics discussion session, as well as some other fun videos like building things and stuff like that that we've done together on stream. Okay, so now let's talk about Maxwell's equations. So there's the differential form. Someone run a poll. Differential form or integral form for Maxwell's equations? I'd be curious to see what people really like to see. So we're going to write the differential form just to have it, because I think a lot more people are more familiar with this. Remember, on our general relativity, we wrote these as tensors, which was crazy. I can't remember it off the top of my head as far as the actual tensor form. But it had like this thing with like this, and like, what was that? And like this thing right here, or something. It was weird. It was nuts. Okay. Definitely not a fan of that one. But we can also write it in integral form. Roll up. Thank you. You guys are the best. Now, in integral form, we have the surface integral of the curl of the magnetic field, dotted with the infinitesimally small area. We should keep with convention and write little a. I don't know why. And that's equal to, now again, we're going to take the current density and do the surface integral of the current, dotted with, again, some infinitesimally small area. Okay. Now, of course, you know that usually you might see something like this to start, and then you can break this down into the normal vector times dA. I guess it'd be a unit vector, but either way. Okay, let's keep going now. For this one, if you know you have a curl and you want to get into a dot product, you can apply the Stokes theorem, as QST was talking about. You can apply the Stokes theorem, and what do you get? You get a line integral over a closed curve times dLb dotted with dl. That looks familiar, right? That's the first half of Amperes Law. Mu sub naught and the surface integral of j dotted with n hat times dA. Now, what is this? What is this? Remember, I said this is kind of just like, you know, the area, right? So we have the current density, and I know this is going to be kind of, this is a little bit hack fresh. This is not at all graduate material, but I don't know how many people have actually taken I love to hear it, Clone Kitty. I love to hear it. I love to hear it. Okay, so if this is the current density. So like I said, this is a little hack, but we can rewrite this as kind of like the current over the area, right? As you might see it. In the graduate school, of course, you want to be a lot more thorough about this. But, you know, this is just some silly stream. So we're going to be silly about it. Now we can say that this is, so we have J is equal to J is equal to that. So then we could also just say that I is equal to, JA. Now, think about this kind of specifically, right, though? Like, the rigor really happens in the following sense, right? You can have some area, okay? And you can have some current going through this area in the form of wires and stuff. You get the picture. And you get some dA right here with a normal vector coming off of it. And this integral is going to take this and blow it up into the size of this shape, whatever this shape is, right? That's what the goal of this integral is going to be. So what you're really saying here is how much current exists inside this shape, right? How much current exists inside that shape. There's another way to say how much current exists inside that shape, right? By just saying that this is equal to the current enclosed. So this is just a fancy way of saying all of the current inside that shape, or current enclosed. So now we have, again, I'm going to rewrite it with S, because that's what we were more familiar with. From Maxwell's equation, starting with this one, and then in integral form this one, we can get, again, Amperes Law very naturally. And this was the way that Maxwell had found it. So we did it! We did a graduate level E&M trick. What do you guys think about that? Are you guys ready for your PhDs? Ta-da!